Gentlemen, gentlemen. Okay, if you guys go last lecture for the this semester, renewable energy, solar photovoltaic systems. Solar photovoltaic systems. Darren and Jeff, did you guys do any of these classes at 292? Yeah, 110. You guys were 110? 110. Okay. Okay, so that's really cool. You can be certified as a solar installer, and there's solar assessor and so forth. So this is, guys, basically when you put a solar panels right on the top of your house or at the building at Dunwoody, and you connect this solar panel generating plant into the grid. So that chapter goes over this one. Really cool stuff, I think. So solar photovoltaic system. So that's what I'm gonna go over and explain a couple of things if you don't mind. A couple of things that I would like to go guys over is the component. What are the components of photovoltaic system? You're gonna see in a couple of minutes here a picture of how the photovoltaic system is put together and tied to the grid. The one that this chapter talks about in particular is called utility interactive solar photovoltaic system. Utility interactive is you cannot run this system unless the utility is there. That's what the utility interactive is. Utility interactive, it only can run with when the utility is there. If you lose the utility, you lose the system. Very, very important to understand. It's not a standalone. We're going to talk about standalone and hybrid and so forth. Utility interactive, you're on your own. If you lose the utility, you cannot run the system. The function of utility interactive system, how it works, and how it isolates itself from the utility. And then we're going to talk about, guys, the NEC requirement. There's a whole article that talks about NEC requirement for the installation and design of photovoltaic system. The installation and the design of the interactive photovoltaic system. So that's kind of the what we're hoping to achieve. And then we'll look at the one-line diagram that has solar photovoltaic system, interactive solar photovoltaic system one-line diagram. How do you build a one-line diagram and tie it to your grid? How do you build one-line diagram and tie it to your grid? So that's basically the whole idea. A couple of things, guys. The NEC code book, Jeff, as you know, you and I know, there's a whole article that talks about photovoltaic system. Anybody remember when photovoltaic system article came to the NEC code book? No, earlier, much earlier than that.
1994.
Oh, 1994, a little bit earlier, 1984. 84. And the first time they wrote NEC article 690, guys, was in 690. It was in NEC 1984. So the reason, so that was in 84. A lot of you probably, some of you were not born in 84. Some, maybe. The reason why it's becoming a big deal right now is because, of course, we're becoming more environmentally friendly, conserving energy, and cheaper product. So that's really what the reason why it's becoming. So there's a whole article about the solar photovoltaic system. There's also Article 705 talk about how do you connect a power plant into the grid. So, but the main article that we're going to talk about this one is 692. So, why it's becoming popular these days? Because of energy conservation, number one, and number two, because of we're more environmentally friendly and cheaper products. So that's just this slide that talks about why it's becoming more popular these days, though it was done in the 50s. Okay, how does the whole? There's a few ways of generating power, guys. Few ways of generating power, electrical power. The most popular one is rotating machines, synchronous rotating machines, right? Synchronous rotating machines can be a diesel engine generator, can be a nuclear plant, use the steam to rotate the turbine, can be a wind, can be to rotate that turbine, does rotation, or it can be the hydraulic plant that same thing, use the water to rotate the turbine. So there's multiple ways of generating power. The photovoltaic system, my friends, is different. Photovoltaic system is completely different than the rotating machines. The way the photovoltaic system is, it takes the sun, the light, so they call photons, particles of the sun, the light, and convert it into DC power. So there is, are you guys okay there? Okay. So it rotates, instead of rotating machines, using rotating machines, it used the sun to convert the sun energy, the energy that comes out of the sun, into DC power, DC voltage, power, and current. So that's the most important difference between the solar photovoltaic system and any other electrical power generation plant. They don't use any rotating objects. There's no rotating machines, no turbines to rotate. So that's a big deal. So you take the photons, they're absorbed by specialized material that you can see, and these materials are called semiconductors material, guys, like diodes and so forth, and it creates electrical current. Most common material that they use for photovoltaic, they call it photovoltaic cell. So there's photovoltaic cell, the photons or the light particles hit the cell, it converts it into a DC voltage and current. You collect these little currents and little voltages and you convert them into a 24-volt panel and 5 amps. So that's how they do these. Here's the material that they make these photovoltaic cells out of it. Special, they have semiconductor materials. Then what they do is they put them in wafers and infuse them with phosphorus gases. So this is the whole production, guys. Long story short, semiconductors, you hit the light, hit the semiconductors, convert it into DC current and DC voltages. You connect these voltages across a load, it converts these DC voltages into a current. Any question, guys, about the method of operation for a photovoltaic system? The single most important one is so-called photovoltaic cell, or crystallized silicon that's made the photovoltaic cells. Any comment, any questions? Any comments, any questions about that one? So that's the bottom line, is you get these cells, you hit it by the photons or light particles, convert it into voltage, connect these voltage together, collect them, 24 volt, put them across the load, get you 5 amps if it's rated for 5 amps. There is no rotating object, nothing rotate, no turbines, nothing. No alternator. So this is a different way of generating electricity. You can generate electricity, as I said, the most common, popular way of internationally generating power is rotating. Turbines, they use turbines. Nuclear with nuclear, or with gas, alternators, or any type of, they burn things, boil water, change it into steam, shoot it right across the turbine, and generate power. That's how they do in Becker power plant here and a lot of other applications. Natural gas they burn. They use the nukes to burn the water. So they burn something to generate electricity. This is no burning. Nothing is burned. That's why it's environmentally friendly. Get that light, dump it across the light particle, dump across the photovoltaic cells, convert this one into electrical current. Okay, so photovoltaic modules. So then when they put all these photovoltaic cells in one big module, they call them, that's where you get your direct electricity from the sun. Then what they do with this DC that you convert, remember we're talking about DC current, then they have an inverter. The reason why we use inverter, guys, because we utilize, your fridge is not DC. Anybody has a DC fridge? There are DC fridges work in smaller applications, but all our equipment are run on AC because AC is more superior to DC system in terms of delivery so far. Delivery and utilization. Transmission, delivery, and utilization. So you use an inverter. That inverter, my friend, inverts the DC back into AC and synchronize it with the grid because it's interactive utility system. Utility interactive photovoltaic system. So take the DC that you generated, invert it into AC at the right frequency and the right voltage. If you have, you can also store some of this energy you can have an out. You take direct some of this energy stored in batteries at night, so you can dump it across your load when the sun is not there. When the sun is not there. So that's basically or overcast days where there's no sun. Okay, here's the single most important component, guys, of a solar photovoltaic system. A solar photovoltaic system is made out of solar modules, and the solar modules make a panel. So if you look at this one right in here, here's my panel. So this is my panel, and my panel is made out of modules. How many modules in this panel? There are 3 modules in this panel, right? And all these 3 modules are tied together to give me a one string. They call it one string. So you have module 1, 2, 3 tied together, give you one string. You put a fuse, you put a diode, you tie them together, and you take them over here to the inverter where you can invert them and tie them to your grid. All these modules together, they make an array of photovoltaic power sources. A solar plant, solar plant, basically. So this is the source of when you see all these panels on the roof. That's how they put these panels. Give you an example. The way they tie these panels, guys, and they've tied in positive. So if these are 3 panels, panel 1, panel 2, panel 3, positive, negative, positive, negative, positive, negative. These are 3 panels. So they go, here's my positive, and then they come from here to this, and from here to this, and from here all the way back. Here's my positive, negative. What you're looking, exactly like batteries, what you're looking at is this string right here, positive, negative. Can you guys see that, how they tie them? Like, exactly like batteries. They add them up. So if this is a 24 volt, Jeff, and this is 24 volt, and this is 24 volt, what's 24 volt times 3? 72? 72. So your voltage here, the total voltage of the system from here to here is 72 volts. Does that make sense? They put these panels in series. They put them in series so they can get you a voltage. So the voltage that's coming out right at this point here is 72 volts. Any comments, any questions? Each one of these panels or modules is 24. Put them in series, positive to negative, positive to negative, positive to negative. Have 2 wires, one positive, one negative. And these 2 wires are equivalent to the points right in here. Can you guys see that? Right into here. Okay, so let's assume that each one of these panels is giving 5 amps. So I'm having each panel is giving 5 amps. I equal 5 amps. If you put 4 panels, guys, 3 panels in series, giving 5 amps, how many amps you get out of the system? They're all in series. All in series. What happened to the current in a series circuit? Stays the same. The current in a series circuit stays the same. So if there is a 5 amps, each one of these panels is giving 5 amps, 5 amps, 5 amps, 5 amps, and I put them in series, the outcome is 5 amps. They're in series. So this panel is actually giving me 24 volt at 5 amps. Okay, so if you come over here, this plant giving me 5 times 24. Adam, what's 5 times 24? 120. So 120 watt. This panel is giving me 120 watt. This panel by itself, because you have 24 volt multiplied by 5 amps, give you 120 watt. Okay? Now, and each one of these, so I have 120 watt. If I have 3 of them, what's the overall of the whole system? So let's just see, I want to have the whole plant here. So I have 3 of them, so 3 times 120 is what? 360? 360 watt. So the whole plant, guys, the 3 panels together, the array here will give you 360 watts. If you need more, what do? You keep adding more and more strings. So that's basically how they do it. Each panel has an amp. This is 24 volt, 5 amps, 24 volt, 5 amps, 24 volt, 5 amps. When you put them in parallel, they add up the voltage. When you put them in series, and the current stays the same. So this panel by itself is equivalent to 120 watts. That's how much This baby is going to give you 120 watt. If you add 3 of these panels, you're going to get 360 watt. 360 watt system. Cool. Any comments, any questions, guys? Any comments, any questions? So now, now remember, guys, there's 5 amps coming out of each one of these. So I have 5 amps here. Remember 5 amps? I have 5 amps here, and I have 5 amps here. So what do you guys think right in here? How many amps you're going to have? They're all in parallel. 15, right? You're going to have 15 amps. 15 amps. You multiply the 15 amps by the voltage that we I'm sorry, this is actually should be more than that. This should be more than that. We multiply, if you take the 5 amps, multiply it by, what's the voltage? 72. Could you please do it by 72? 5 amps times 72, because the voltage is 72. What's 5 amps times 72?
360.
360, thank you. 360, that makes sense. 360 watt. And then when you multiply so with each one of them is going to get 360 here. 360. 360 watt. So you take 3 of them, right? Each one is 360 multiplied by 360. Now that makes sense. What's the 3 times 360? 1080 watt. Thank you. So this plant is 1 kW. This plant is 1 kW. This plant is 1 kW. So if you take this one, multiply it guys by 72, can you guys check if you get 1080 watt out of that? So that's how much watt, 1K. This plant will give you 1 kW, 1 kW, DC, 1 kW DC. Any comments, any questions about this DC photovoltaic system? DC photovoltaic system. Any comments, any questions? One more time. When you put the panels in series, the voltage will add up. The current stays the same. The watts for the system is the amp multiplied by the voltage, give you 360. So basically, that's how much power you can get out of this plant. Okay, a couple of things, guys. So this is your photovoltaic system. They have another system that they call it DC. The top one, guys, is DC. The bottom one is AC. The AC, they have panels that the panel itself have then what they do right here is they take it to the inverter. They take it to the inverter and they invert 1 kW. They invert 1 kW to the right voltage and the right frequency. 1 kW to the right voltage and the right frequency. 1 kW to the right voltage and the right frequency. Any comments, any questions, guys? I want to bring to your attention, each one of these is called the string. Each one of these right in here is called string. So how many strings do I have? 1, 2, 3 strings? Strings. Strings is 2 wires coming out of a channel. That's called the strings. Then when you tie the positive to the positive, the negative to the negative, that becomes your string 1. This is string 1, string 2, string 3. Do you have to have a fuse? Can you guys see that there is a fuse here to protect the string, the DC, AC string right here? You have to protect it with a fuse. There's also diodes, Jeff, and the diodes here is to protect this panel from feeding current into the next panel, or one string to feed current into another string. If you have a short circuit right here, say you have a short circuit right in this panel. Do you really want the 2 panels to dump power, come from here and go right in here? Come from here and go, the current goes this way? You don't want that to happen. So the smarter than Chad decided to put diodes. Diodes will block it. So the only way that this current can go is only one way, right? Only one way, coming out to this way. This one, the same thing. This way, this one, this way. Why? Because of the diodes that they're putting in this DC circuit. Because of the diodes that they're putting in this DC circuits. Any comments, any questions? So that's your solar photovoltaic system in a nutshell, basically. Panels with a voltage and amps. You series the panels, you get to a higher voltage. You can see add the voltages. The amps, these are rated. The panel will come 24 volt, 5 amps rated. You multiply them, you get to the power. You have, if you need more power, Then what do? You keep adding strings. So how many strings do I have? I have 3 strings here. 1, 2, 3. 3 strings. And all together, I don't know if you guys can see blocking diodes here to block the current from going to another one. The output right in here is called photovoltaic source circuit right here. And when you group them, it's called photovoltaic output circuit. Photovoltaic source circuit, photovoltaic output circuit. Any comments, any questions? This system here is called DC system. DC system. This system here is AC system. AC system, the only difference, Jeff, is they have the inverter as part of the panel. The inverter here is right in here. They put the inverter right here, and they actually tie together AC circuits in sync. So string 1, string 2, string 3, instead of being here, these are AC, and instead of these are DC, right? The time you get AC is right here. AC is converted right at this point. This is where you get your 240/120 volt. Right here, you get 240/120. I'm just picking this voltage right at the output of these panels. Right at the output of these panels. Any comments, any questions? The most common one, guys, is the DC system here. That's the most common one, but they also have an AC photovoltaic system. How do you buy an AC? The panel itself has to be bought as an AC panel with an inverter with it. Inverter right at the panel. Tiny little device that they invert right at the level of the panel.
Will it come with it if you buy a panel?
If it's an AC panel, yep, it will come with the inverter with it. And then you just group them together. You group them together. So that's basically what the system is. Speaking of, then when you grab in here photovoltaic sources, so this is coming from string 1. You guys remember that one? This is coming from string 2. These are all panels. This is coming from string 3. Each one of them has 5 amps. 5 amps. Out here will be 15 amps, and the voltage that we just used a second ago is 72 voltage, 72 volt. You put it through an inverter. Can you guys see the inverter here? You put it through an inverter, and it inverts it back into, let's just say, a 240/120 volt system. And that's how you tie it to your equipment. This is the system that they call utility interactive system. Utility interactive system. Any comments about the riser or one-line diagram for utility interactive system? Each one of these panels, guys, are, just example, is 24 volt at 5 amps. 24 volt at 5 amps. This string here can give me 72 volt at 5 amps. Each one of these strings, when you add them up here with the diodes and the fuses, they end up with 15 amps at 72 volt. When you go through the inverter, it inverts it back into 240 at the right voltage, at the right amps. Any question, guys, about utility interactive system? Utility interactive system, Zach, works only if you have the electrical utility. If you don't have an electrical utility, this system will not work. This system will not work.
Why?
By design. By design. By design. Even later on, what they do with this inverter, if you are to tie the inverter into the grid and sell back to Excel, if Excel's to go down because a storm came and hit the transmission line, they want you to feed back and kill one of their electricians. Safety. So if you want to sell to Excel or any power utility, you have to have something called interactive. Part of, we'll talk about this in a second, part of the requirement, utility requirement, to allow you to tie to their grid and sell back to them is to have a function that shut down your utility, your inverter, upon the loss of the power. So they will be sensing the power here. If the power from the utilities is gone for whatever reason, then they shut down your inverter. Now, there are inverters that shut down this inverter, but they have a bypass that can go and direct you into another inverter that can, separate inverter that can get you back up. That's a whole different story. You know, you can have a bypass right here that can get you into your batteries, dump it across your batteries and invert it through your batteries. Okay, there's another standalone system. If you live in a bony land and you want to be off the grid, here's what you do, guys. You have a solar photovoltaic system. You have a battery charger. Here's your system here. All your panels are coming in here. They tie to the charger. The charger will charge the energy storage. That's your batteries. And then from here, you invert the power into AC so you can feed your house. And you also can feed DC. If you live in an area where there's no grid, right up in the mountains, you can go put a bunch of panels here, get your 72 volt or say 300 volt, invert the voltage into 24120, feed your house. But because you don't have a grid, at night, what are you going to do? You need to have batteries so you can charge the batteries during the day, and at night you can invert the power coming out of the batteries into AC and dump it across your house. This is called standalone system. This system is called standalone. There is no utility. The third system, so these are three systems. System 1, System 2, System 3, guys, is when you have a hybrid system. You have a wind or a generator with the photovoltaic tied together, and then you can an energy storage sources and chargers. So you have wind and solar tied together with batteries, inverted into AC and feeding your house. No grid. Hybrid, you have a generator, diesel engine generator, and you have a wind turbine, and you have a solar, all tied together at one point. Then you can have backup. Then you can have a DC load. You can feed out of it from a DC load, or you can invert it and feed an AC load. The most common one right now, is the top one, for one reason, because the federal money, which is drying as we talk, the whole solar system federal money is drying. There was tons and tons for the last 5 years, guys. There were tons and tons of dollars in federal dollars for people who want to invest in solar photovoltaic systems so they can feed to the Excel and get off the grid, basically, and feed to Excel. So that's photovoltaic system interactive is the most common one. And the reason why it's most common, because most of us live in urban areas and we have a grid anyway. All what we need just to offset our bill, electrical bill, and so we don't pay that much. And with an agreement with Excel, maybe sell them some. So you have to have bi-directional meters that goes with it. If you are consuming more, producing more than you're consuming, certain amount of power will go into the grid so your neighbors can use it, and you will be paid for it. Any comments, guys? Any question about these one-line diagram or risers? One-line diagram for the system. Jeff?
You know what's a common price to get paid? You know, like versus kilowatt hour that you actually pay, like yourself.
They make it, gosh, there's a different, I can't remember off the top of my head all the agreements, but there's agreement between Excel and it's getting, here's what Excel wants you, like electrical utilities, they want you guys to offset your load, but they also don't want you to get into the business of producing power. Why? Because they're making money. So they want to use the federal government is mandating, and the state governments are mandating utilities to have certain amount of their loads from a green energy. I think in Minnesota, 30% by 2014. I can't remember. There's 30% of their power by Excel Energy in Minnesota have to be produced by green energy, wind, solar, hydraulic. So then in order to get that 30%, otherwise they'll be penalized by the government, they encourage the customers to invest in solar photovoltaic systems so they can get credit for it, the utilities. Now, when they reach their credit, they don't want you to invest more and get into the business of generating power because you're going to get them out of business. As a matter of fact, so for years, the utilities have given a lot of money for and incentives. Lately, utilities themselves are getting into the business of solar photovoltaic systems. So they go into places where there's a lot of sun, Arizona, and they build plants, big plants that makes megawatt in solar and dumping it across the national grid, so for all of us to get it. So there's a whole lot of agreement. Long story short, right now, what I can tell you that's true is if you want to have a solar photovoltaic on the top of your house, they allow you to offset your load. You can pay zero for Excel, that's okay. Now, if you want to generate more to sell them, they make it so cheap for you that's not worth it to sell them. But you can offset your bill though. You can pay $0 for them. But they make it, when you produce more, you're basically producing cheap energy for them. They make the price so cheap because they don't want to, they just don't want you to get, they want you to get off the grid, fine. But they all don't want you also to help your neighbor getting off the grid and everybody.
So they'll buy your
There's
extra,
business.
and it's better than nothing if you have extra power, but.
Yeah, but the price, my understanding right now, and I'm not an expert in that, the price is so cheap, it's just cheap to sell them. But remember, you still can offset your bill. So that's the whole idea, guys, of doing it. Modules. So talking about the solar photovoltaic system, the building block of the solar is the solar module, like we talked about. What do they do? They have photovoltaic semiconductor cells or photovoltaic cells electrically connected together to make a unit. All these cells are tied together, guys, in to make a unit, and they put them in a big box. And they have different sizes, as in watts, and different efficiencies, and of course that with this come a cost. So that's why you can buy right now a 300-watt panel, one big fat panel, 3 feet by 2 feet, and can get you 300 watt, one panel at 24 volt. So with certain efficiency, What they do with them, guys, they also come with lead wires. Anybody have wired them? If you wire them, they come with lead powers, plug them in. What they do, really easy to do it. Here's one panel with this wire, and male. This is male female, and this is another panel here. The same thing. And this is, if this is my positive, negative, positive, negative. What they do, guys, these wires are long enough that they can take your positive, where's my positive, right here to my negative, and then come up with here with the system. So they can tie with wires. They come with strings of wires plug in. They plug them into positive, into the negative when you series them to get you the voltage that you're looking for. They come with wire leads. Jeff, did you guys wire them when you took your class? Wire fuse them?
We just did, it was kind of in conjunction with solar voltaic.
Okay. It wasn't the actual wiring.
Class. The hall has a whole system. They've got panels on the roof. Yeah, they've got a windmill up front.
Yeah.
And a bunch of other stuff. So we can actually see, what the inverter and what the setup looks like. And they have a panel view inside that shows,
how the consumption and so forth.
Generated at that time.
Okay. So, yeah, absolutely.
Yeah.
Then what they do, guys, what they also do is they have all these panels sit together and they make a generation plant. Generation plants, that's when you group it together and you get your 10 kW, like residential 10 kW worth of power. There's something called combiner box. That's the box where you see the diodes and we were just looking at diodes and fuses. That's where you put your series connected strings. You put the strings of modules connected in parallel to make to other strings. So they have diodes. They have the diodes and they have fuses, and they put them in a box. You'll look at them in a second here. That's how they group them. The NEC code book, guys, require disconnects on the AC and the DC side. So if I have an inverter here, my inverter, I need a disconnect on the AC side. This is my AC side. I need a disconnect in my DC side. Here's my DC side. So you required disconnect sized on the AC and the DC side. AC and the DC side. So that's your disconnect, AC, DC. Inverter, what does inverter do for a living? It takes the AC, invert it. So I have a voltage that looks like this. I invert it back into a voltage that looks like this. That's what the inverter does. Invert DC into AC. DC into AC. And this is, Jamie, my friend, this is the most important thing. If it's an interactive, automatically synchronized to the utility system. Because when you guys generate power, you have to synchronize it with the grid. Otherwise, the grid will push you and burn your equipment if you're not in sync with the grid. So the job of the inverter, guys, is to monitor the grid and see what's your voltage, 480, yep, we'll generate it 480. What's your frequency, 60 hertz, yep, and synchronize the output of the inverter with the input of the utility, with the input of the utility. Any comments, any questions, guys, about disconnects and inverters as part of the photovoltaic system? This is where the requirement by code and by UL 1741, and the code requires that one. If you have a photovoltaic utility interactive, this particular type, not the standalone, utility interactive inverter, it requires you, my friend, to, they call it anti-islanding. It requires you to turn off when the power is lost. Anybody knows why? Because we don't want to kill journeymen or linemen, people working on the grid. So if you lose power, part of the agreement with the grid, if you are to have an interactive, not a standalone, is to have the anti-islanding, which means the minute that you see there's no power coming to your plant, you have to shut your inverter off. You have no power, basically. They also require you, the NEC guys require you to have a DC ground fault protection. What happened, Jeff, is if you have a ground fault in a module, how are you going to monitor these? The current is so small. So the way they do it, they make the conductors so thick and big enough that they can handle the ground fault, number one. Number two, but we don't want the ground fault to sit there. So you have to have a ground fault protection, DC ground fault protection that looks at any ground fault between the positive and the negative, or the positive and the frame of the panels. And if you have a ground fault, it will trip and isolate the system. It will trip and isolate the system. Safety, ground fault. In 2011, because of fires created by arcing on the DC side, in 2011, they start requiring the solar photovoltaic system to also have an arc fault protection, DC arc fault protection. So what they do, guys, the inverter, they have inside the inverter, they have an electronic function that monitors the arc, like arc fault circuit interrupters. And if there is a signature that coming out of the DC that looks like an arc, it will isolate the system. Jamie, my friend, it will isolate the inverter, and basically there's no longer current. This is required on any system of a voltage above 80 volts, 80 volts or above, that particular one. Any question, guys, about the GFCI or the GF, ground fault protection and arc fault protection for the DC part of the solar photovoltaic system? DC part. They use the GFCI ground fault protection. They use a fuse that they trip that fuse. Arc fault circuit interrupter. They use a part of built into the function of the alternator, into the inverter. Okay. What they do, guys, also with when you do a plan, they have site or plot plan. When you do your solar photovoltaic system, these are big. So what they want to do is you want to have a site or plot plan where you can lay out your solar photovoltaic panels, your solar physical and mechanically lay out your solar photovoltaic panels, and you show the connection of these panels, right? So that's what they call it, the site or plot plan. And then they're going to show where the utility is located. So here's my utility. In this case, it's located right in here. And this is how I'm going to tie to the utility. So it shows the physical mechanical layout of the system, as well as how it's going to be tied to the inverter. That's, they call it a site or plot plan. Single line diagram and schematic diagrams. This is the one that we were just looking at. They call them single line diagram. How are you going to tie to the grid? All the stuff that we looked at, these are called single line diagrams. How this system is going to be tied to the grid. So they have a single line diagram that represent how the system is going to be tied into the grid. Here's a good example, a more detailed example, guys, how the system is tied. Here's all the modules. Can you guys see the positive is fused? We have a disconnect. We put it across the inverter. we invert at the right voltage, right frequency, and we dump it across the panel. This is your riser or one-line diagram. In this case, one-line diagram that shows the details of your system. Any comments? Any questions? Any comments? Any questions? So that's your riser. Let me see what the voltage on these particular ones. Then a couple of sizes. This is a good place, guys, to do a couple of sizing. The way they do the size, when you size your conductor, the DC conductor here, very easy. They take something called they take the I short circuit of the module. You take I short circuit of the module and they multiply it by 1.25 and multiply it again by 1.25. And that's how they size that DC conductors. That's it. Twice multiplied by twice to accommodate for the short circuit and the continuous load. That's how they size your conductor. In the AC side, they take I in for the inverter and multiply this by 1.25. That's how they size the conductor here, as well as the overcome protection device, as a matter of fact, as well as the overcome protection device. Same thing here, as well as the overcome protection device. They size them. So that's really the bottom line is the way they size the conductors on the DC side. They take the current, remember the let's do the 5 amps. For example, the 5 amps that we did, the 5 amps are the short circuit rating of that conductor. So here's 5, multiply this by 1.25, multiply it by 1.25 again. Can anybody do that one for me, please? 5 times 1.25 and times 1.25 again. What do you get? 7.8 amps. That's good enough. And then your conductors, in this case, the minimum that we're going to be using is number, let's say number 12 conductor, right? And the overcome protection device is 10 amp fuse. So we have a 10 amp fuse and a number 12 conductor because we don't want to go for voltage drop. There's also voltage drop issues. You don't want to lose anything less than 12. So that's how we size the conductor here. Now when you came out of here, let's say the inverter, let's just say the inverter amps we're inverting, say 10 amps, multiply this one by 1.25, gentlemen, you get 12.5. Your conductor here is going to be number 12 again, and your circuit breaker here, what's the next standard? 12.5, 15 amps. So that's it. That's how you size the circuit breaker for the solar photovoltaic system. On the inverter side, the input and the output. The most kind of weird thing is the multiplication by 1.25 twice. And therein they do this to accommodate for the short circuit and the continuous load. They want the conductor to carry the short circuit current inside the panels for an unlimited amount of time. So they oversize the conductor twice. They multiply it twice. Any comments, guys? Any questions? Any comments? Any questions? I will draw to your attention. You have to have a disconnect here for the array as well as the inverter. You have a disconnect here. When you tie to the grid, also you have to have a disconnect right to the grid. That could be the circuit breaker is your disconnect. You have to ground typically the neutral, the negative. The negative is grounded right here. The negative is grounded. And then, Jeff, the AC system is also grounded, and you need to tie the two together. Can you guys see that? How to tie them together? Typically, all these systems, guys, typical. They have to be all bonded, tied. When I say tied, bonded. So this typical. I want to say typically minimum number 6 AWG, and this one is typically number 6 AWG. And I don't know if you guys can see the ground. There's also a ground wire. There's a ground that's coming out of here. Can you guys see that? Ground all the way and grounding all these modules. What they do typically for this is they use number 6 AWG, and everything is copper. Everything is copper. That's how we size the solar photovoltaic system typical application. Grounding electrode conductor is number 6 for all of them. We size the conductor number 12, number 12. Overconduction device, we have a 10 amps on the DC, 15 amps on the AC. You have to have a disconnect on the DC side and a disconnect on the AC side. These act as your disconnect. When you tie to the utility, you have to have also a disconnect if it's not within sight. Sometimes you have one disconnect here for all of them. If they're within sight, within 50 feet of each other, and with no obstruction. Otherwise, if this is behind the building, you have a disconnect as you tie it to the grid. Any comments, any questions about the one-line diagram, guys, for the system? One-line diagram for the system?
And then all THHW wires.
THHW wires, wet location, absolutely, typically. In the AC side, if you're inside, you really can't get away with THHN. If you're inside, depends where you are. Typically, you're coming from outside to inside, wet location, THHW. Absolutely. Really straightforward, no gimmicks in that system. Any comments, any questions? This is where the Excel come in. See, this is your 100 amp, and you say you're going to put a 20 amp and tie your house into the grid. You backfeed the 20 amp circuit breaker, backfeed it, and the circuit breaker acts as your disconnect, approved, or you put a disconnect outside. Any comments, any questions, guys, about how the system is tied to Excel and how do we size it? There's one little thing, Jeff. I think these are 24. Yeah. Let me just do the math on. If you guys look at these modules, I have 4 at 28. Can you, Jimmy? Can you take 4 multiplied by 28? Give me what's the voltage on this system? 4 times 28. How much? 100. Is it somewhere here? 112. 112 volts. Okay, so this is DC voltage. DC voltage 112. Now, believe it or not, guys, modules. The colder the weather, the more voltage they can give you, and the better they perform. The colder the weather. Now, who's better than the state of Minnesota to talk about cold weather, right? So there's a table in page 489. It'll tell you what's the lowest temperature that this panel is going to encounter. In Minnesota, if you look at page 489, the lowest temperature that they can encounter, ambient temperature in Fahrenheit is, let's just say, minus 31. Would minus 31 in Minnesota be minus 31 Fahrenheit? They don't go, guys, by the, really, they don't go by the lowest. They go by the statistically lowest. So if there's actually has statistically value, so if it goes, it dips down for minus 40 for a couple of hours in the middle of the night.
Down here, probably minus 20.
Minus 20.
Tops.
Okay, let's
minus 35.
let's just say right here minus 20. Did you say minus 20? If you guys look at the table, minus 20 will give me a multiplier of 1.21. So because it's minus 20 degree Fahrenheit in Minnesota and Minneapolis here, what they want you to do is they want you to take this voltage and multiply this one from the table by 1.2. Okay, Jamie, what's 112 times 1.2, please? 20, 1 second, 21, I'm sorry, 1.21. 1.21.
Probably 135.
Anybody? I need a calculator though. 135. 135 points. 0.5 volt. Okay. So what I want then this is becoming the voltage rate, the rated voltage for your system. This becomes the rated voltage for your system. Any comments, guys? Any questions? This becomes the rated voltage for your system. So the voltage have to be adjusted based on the temperature that you have. Based on the temperature. We have to adjust the voltage based on the temperature, period. Any comments, any questions? When you design the system, you have to adjust the voltage based on the temperature. Where did I get this 1.21 based on minus 20 Fahrenheit in Minneapolis, and it's table 690.7 in the NEC code book or in page 489? Any comments? Who cares? The question here, Jeff, who cares, right? Who cares? Your conductors have to be rated for a certain voltage, right? 600 volt typically. What if you build the system and when it's summer, the voltage will be within 600 volt. In the winter, because of the multiplier, the voltage exceeds 600 volt. So you might, if it's exceeded the insulation, then it becomes dangerous. The voltage can run away from the conductors into surroundings. So your insulation is not rated for the voltage. That's why it becomes a big deal. Any comments, guys? Any question about the voltage rating of the system? This is DC, by the way, on the DC side. How do you size the DC? 1.25 times 1.25 short circuit. And the voltage that they use, this voltage here, guys, it's called V open circuit. They call it the open circuit voltage. What's an open circuit voltage? You have a panel and you measure and you don't have any load across the panel. You just measure the voltage. That's called open circuit. The highest is the open circuit. What happens if you put a load? The voltage dips slightly. So you use the voltage open circuit, Jeff. That voltage here is called voltage open circuit. And the current that we use when we size on the DC side is I short circuit. Meaning, here's a positive and a negative. I'm a panel. Tie the positive to the negative. That's the positive to the negative of one panel. The panel must be able to handle this current, to handle the short circuit current. So the conductors cannot melt. Because they're on the roof, guys, how are you going to disconnect them? There's no disconnect for the actual panels, right? What if one positive touch a negative on the roof, right? So the conductor starts feeding into the panel. The conductor and the panel must be able to handle this without creating a fire. Okay. We talked about calculation. When you do calculation, we always use V open circuit, like that 28 volt is V open circuit. Maximum, the maximum DC current is typically when we size I short circuit for the panel. These are for the panel. AC calculation, guys, it's the input of the size conductors and components based on the input of the inverter output because they're coming out, and 1.25. There's ambient correction that you have to do if you are in the roof. You also have to size, take into consideration if you're on roof, you have to derate because you put conductor on the roof, they're exposed to two temperatures, temperature direct and temperature reflected from the roof. So that's basically the calculation that we do. Then they get into the mounting. There's a lot of hardware, guys, ballasted system, bolted system. There's a lot of hardware. Typically, either they ballasted it, they put loads on it, or they bolted it to the roof so it doesn't move, and they put your array on it. You have the mounting ground. Typically, the panels run like this, and they run, not like this here, and they run a grounding conductor right underneath it, and they tie each panel to it, and they go to the ground. This is typically number 6, copper. Because of lightning and everything else, they take each one of these panels, guys, they tie it right underneath these panels, and they pull them all the way to the ground. Combiner box, that's where you bring the string, guys. The string, your string, you bring it and you put the diodes. Remember these diodes business and the fuses. You bring the diodes and the fuses and you put them in that combiner box. Wiring, any wiring that rated for outlet location can be used. Grounding electrode system, you have to create a ground rod right by the system, guys. If it's on a roof, you tie it to the grounding electrode system. If it's outdoor in the parking lot, you have to create a ground rod, tie the modules and the frames to it, and tie it back into your grounding electrode system of a building. So that's a few things about that system. Utility point of connection, labels and equipment marking. We'll talk about this one, guys, in a second. When you tie to the electrical utilities, let's talk about labels. Your system, guys, have to be labeled. The labels and signs. All your wires, Jeff, all your conduits that's carrying solar photovoltaic system have to be labeled as solar photovoltaic system feeders. So you don't cut into them. They don't have a whole lot of protection. Your disconnect the DC have to be labeled as solar photovoltaic system. Just a label. Inverter have to be labeled. Everything associated with the solar photovoltaic system have to be labeled on the AC and the DC side. Disconnects, inverters, as well as feeders. Disconnects, inverters, and feeders. Can I have thumbs up, chat? Labeling? Cool. Then the second thing is utility connection. How do you connect with the grid? There are two ways of connecting to the grid. There is the rich man's way, Chad's way, and the poor man's way, Zach's way. Is that insult or can we use that one? Okay. There's the poor man's way and the rich man's way. The poor man's way, guys, very easy. You can come, can you guys see the meter here? The meter right in here, this is where Excel gets you the meter. You can come on the line side of your disconnect. So this is your 200 amp disconnect for your house or for your building. And right on the line side, and you tie your power, you put your disconnect here. You have to have a disconnect and a fuse disconnect. And then you tie your solar photovoltaic system right at the line side of the disconnect, between the meter and the disconnect. That's called the rich man's way. No limitation in how much, no limitation how much current you can pull here. You can put as much current as Excel allows you to, right? So if you have a 200 amp, I can put a 400 amp push back into Excel. Granted, the wires are rated to do. Wires are rated, right? Because you have to push back through the wires. If you have 200 amp wire, you can't push a 400 amp into it. So there is no limitation how much power you can go through this system. No limitation whatsoever by code. The only limitation is how much current the utility is going to limit you, of course. Can I have thumbs up, Chad? No limitation if you do it this way. Let's talk about the poor man's. This is a rich man's way. That's typically how they do it, guys, with major commercial customers. That's the best way to do it. Right on the line side, right in here, the line side of the disconnect. No limitation how much power you can. So by the way, the power, so if you have 200 amp, what happened is, and you're generating 400 amp, 200 amp will come right here to feed your building, to get you off the grid, and the other 200 amp, guys, where does it go? 200 amp goes to Excel. So now you're selling Excel 200 amp, not like they will allow you to do that, and you're consuming 200 amps that you need. Cool? So your meter here is bidirectional. Your meter can meter this way or can meter this way. Bidirectional. The meter can rotate in both directions. Has Excel have to be involved in that one? The electrical utilities that you do have to be involved in that one. They put a meter for you, and they can limit you how much you can push back into them. They will never allow you to push this amount, up to my knowledge, unless you have an agreement with them, because now we get into the business of production and all this good stuff. Any comments, any question about the supply? They call it the supply side connection, So piece of cake, your supply side connection. We'll talk about the load connection in a second, guys, because I don't have the picture. I'll show you in a list in a second here. When you finish your system, guys, when you build your system, there is a commissioning. They call it commissioning. You do commissioning. So before your system, you have to go check all the connectors are there, all the disconnects are labeled, all the wires are stable, and all this good stuff. So you do commissioning in the building, and you go readjust your interactive inverter. You have to readjust your interactive inverter itself. Calibration. There's some calibration that have to be done on the inverter to attain maximum performance. For example, when you lay out your panels, do you think you just sit your panels in any direction? There is the optimum location and direction and tilt for the panels to get you the best performance. So these are all commissioned. It becomes really more, yeah, you have to commission the building to get you the best performance of these panels with the tilt. So that's before you energize and you get your system. I'm going to go directly to a couple of pictures I'm going to show you here. That's basically it in a nutshell. Any comments, guys? Any questions? The single most important thing is this diagram directly from Article 690, 90. And it will tell you how the system is put together. This is called the combiner box. They call it combiner box. These are your panels. This is your panels, and then come over here. You have inverter, and then you have really easy. You have a disconnect here, and then you need a disconnect here, and then you dump it across your panel. Very easy, very simple. Here's my meter here. my meter, here's my panel, and you dump the power right across your panel. That's how the system is put together. Very simple, very easy. No rocket science. That's this system, the most common one. So everything up to this point, guys, is DC right here. This is my DC. And then after that, everything from here down is my AC system. Can you guys see how the two systems are tied together? The two systems are tied together. The DC inverted, tie it to the AC. Okay, so that we talked about this one. Let me show you the last thing. Okay, here you go. Okay. So we talked about there are three systems: interactive, the most common; hybrid, multiple sources; and standalone. If you live in a boony land, you want to get off the grid. We talked about this wiring. I can take this wiring right now and wire any system exactly based on this. I want to emphasize therein the positive is fused, the negative is not. As you bring it to the inverter, this is called one string. Out of the inverter, you put a disconnect right here, and then you tie to the grid. A poor man's way or rich man's way. Here's the poor man's way. The poor man's way of doing, like we talked about the rich man's way between the meter. The poor man's way, guys, is you tie in a disconnect at 20 amp. The 20 amp. So you put a 20 amp right as a feeder. And if this is 100 amp, then the bus here, 100 amp, you cannot exceed more than, so there's limitation though. Here's the limitation. Do you see that bus here? The bus, the size of this bus, guys, when you add 100 plus 20 equal 120 amps. So you cannot exceed more than 20%. If this bus is rated for 100, it's 100 amp. You cannot exceed more than 120% of this bus. That's the drawback. The drawback of doing it the poor man's way. Take this. If this is 100 amp, I can't exceed more than 120% on it. So what's 20% on 100? 20 amp. So this has to be a 20 amp. Another example, the poor man's way. If this was a 200 amp, okay, and also this bus is 200 amp typically, 200 amp. Now, what's the largest size that I can get out of that? Double this, 40 amps. 40 amps. How do you know, Chad? You take the 200 plus 40, that will give you 240 amps. 240 amps. And then 240 amps must equal 1.2 times 200. Is that true? Is that true? 1.2 times 200, 240. You guys see how you get that? So why it's called the poor man? I call it the poor man's way because you're limited. How much you can push through the system? How much you can push through the system? See the limitation? You're limited on the size of the main. You only 20% on the size of the main. That you can push only 20% of the size of the main and the buses. So that's why this is limited. Typically residential, they do it this way. Therein, if you have a 100 amp panel, you tie a 20 amp circuit breaker, double pole 240, and you tie all your grid. If you have a 200 amp panel, they use a 40 amp circuit breaker. You put it right there at the bottom. They put it at the bottom of the panel. Anybody knows why they put it at the bottom of the panel? Because the power can be distributed between the two sources. Now I have two sources, one at the top, one at the bottom. I can easily suck current from both sides. You don't want to put it at the top here. You don't want to put the circuit breaker here. You can overload that bus. Any comments, guys? Any questions? Any comments? Any questions? So that's your poor man's way on the solar photovoltaic system. Solar photovoltaic system. So limitation of 120 times, no more than 120 of the bus rating on this system. Okay, here's the rich man's way, and you can see there's no limitation on that one. Here's your solar photovoltaic plant, generation plant, how it looks like. Here's your combiner. I don't know if you guys can see. These are all the fuses coming out of the strings, and they're all tied together All of them are tied together. Can you guys see that big black boy here? That's your positive. The white is your negative, and you have a disconnect for your system. So you're fusing only the positive here. You have to disconnect. You have to have a disconnected inverter, guys. You have disconnect right next to the system. You pull your powers on the roof of on the building. Obviously, then you have to derate. Jeff, if you put them on the roof of a commercial building based on the height, can you guys see the height? You have to derate, do some derating here. If you mount them outside on the ground, then you have to drive a ground rod and tie them all together. Here's when we talked about Minnesota, guys, how to increase the temperature. And Jamie, my friend, said let's use 120. Here's the number that I got right here, and here's a 1.25. So if your voltage is 100 volt, then you multiply it by 1.21 times 100. That gets you 121 volt. That's to accommodate for the panels will push more voltage. To you as it gets colder. It will get more voltage. Semiconductors will work better when it's cold. They give you more voltage. So to accommodate for this, you have to multiply by a factor. If you put your system on a roof, you have to derate based on temperature, and I hope you guys know how to use that. If the ambient temperature in Minnesota is 90, and I put them 20 inches off the ground, then I add 30. So 90 ambient temperature plus 30, that gets you 120 volt, 120 degree Fahrenheit. These are all Fahrenheit. That's the temperature that you need to derate your conductors, your AC and DC conductors by on a roof. Okay, so that's your adjustment factor if you do them. And basically that's about it, gentlemen. Any comments, any questions about photovoltaic system? It's a great skill to have. Really no rocket science. You have enough information in this chapter to really get you to design, get you started in designing as well as installing a system. Really no rocket science. The only difference from what we have done before is you multiply the DC by 1.25 twice when you size the cables. And you use the open voltage and you adjust the voltage because of DC, because of the temperature. That's really the only thing, and a lot of disconnects everywhere, and labels. Any comments, guys? Any questions? Any comments? Any questions? Would you be up and running with the solar photovoltaic system? No chat? No, thank you. Like we say always, Jeff, my friend, and Adam and Andrew and Kerry, this is another tool in your toolbox. Another tool. When you guys graduate from Dunwoody, our job is to get you not to be a one-shot gun. You need to be a multiple shotgun, right? So that will diversify your knowledge in how to design different systems. That's what this chapter is all about. It's giving you an alternative. So please read it. Please do the answer the question for it. It's a great way of getting in a solar photovoltaic system. If your company is designing a system or installing a system, you know a few things about it, I hope. Okay, thank you.